I think we are on. Okay, that means one more time, welcome at the first session in week 8. And this week we will talk about the limits at infinity and horizontal asymptotes, which is today's session. And then section 3.5 is just the summary of all of the information that we can get from the first and the second derivative and get the graph of the function. That means section 3.5 is like a accumulation summary of all of the information from chapter 3. Okay, but before that, we have to know how to compute the limits at infinity, or using different words, I can say limits at infinity are the end behavior. Even in the pre-calculus classes or algebra classes, we also talk about the limits at infinity. Maybe we're not really naming like limits and infinity, but we're testing how function behaves at the end of the domain, and if the end of the domain is in positive infinity and negative infinity, that's simply a limit, the behavior at infinities, positive or negative. And computing a limit at infinity, the conclusion is horizontal asymptotes. Okay? That's when we'll try to combine these together. I'm sure we know how to compute the vertical asymptotes. I will, of course, remind you a little bit between this, during this session, but the point of this, the whole session, you should be confident finding horizontal and vertical asymptotes, and of course, computing a limit at infinity. Okay, that's me. Let's start. What we have, let's see. In chapter 1, I don't want to show you everything. What we were looking like before. Before, we were looking at something that we will call infinite limits, right? We can see infinite limits. Of course, we still can't really see the infinity here, but we remember having a rational function and trying to find how this function behaves at the number that is not in the domain. In this case, it's for 3 minus x over 1 minus x, the x equals to 1 is not in the domain. That means if the number is not in the domain, we may have like a vertical asymptote, we may have a hole, we remember, like removable discontinuity, and what else? Actually, that's pretty much we may have different kinds of discontinuity. Okay? Because we may also have a jump, but sometimes the function is defined on one side. But actually, even if the number is not in the domain, we may have a jump discontinuity. Okay? Let's check what kind. And computing this limit, we will simply substitute 1 at the moment. That means 3 minus 1 is 2, 1 minus 1 is 0. As soon as we have 0 in the denominator, that's not right. We know that the final answer will be undefined. But what we know, this is not really 0, since this is not really 1. Okay, let me make nicely the whole screen. Okay? Because this x is not really 1, it's like 1 from the left-hand side. And 1 from the left-hand side is 0.9. 1 minus 0.9 will give me tiny number, but positive. And we remember 2 over small number, let me just do, is simply a huge number. Yes? A constant over small is big. And this one will be on the other side, 1.1, which 1 minus 1.1 will give me tiny number, but negative. And then the answer is negative infinity. Okay? As we can see, that's what I was saying, infinite limits. That means, please remember, when we're looking at the behavior, again, of the function near to the point that is not in the domain, okay, we may have, as I said, removable jump discontinuity, or we may have infinite discontinuity. Infinite limit is showing me infinite discontinuity, and this is always the way to find a vertical asymptote. Actually, this is maybe this way. This is telling me that we have vertical asymptote at that number. Okay, that means limit. If the limit is infinite limit, this will be the vertical asymptote. right? Because later you will ask me, oh, how can I find the vertical asymptote? Remember, find the numbers, zeros of the denominator, which means the numbers that are not in the domain, and compute a limit. If the limit is infinity, then yes, this is a vertical asymptote. If this limit will be a finite number, okay, like, I don't know, let's pretend 5, then I will know that at 1, the limit is 5. And the limit exists, let's say both of them, of course. Right? That means we may have this, and then it's not a vertical asymptote, even if the number 1 is not in the domain. That means make sure that you always have infinity. Okay, we do not have 5. Okay, and then vertical asymptote. So I can possibly draw this. That means at 1, just at 1, we can see on the left-hand side, function goes up to the positive infinity, and on the right-hand side, function actually goes down. It probably is the graph, but we can see at the near to the asymptote, we can have the behavior. Okay. But this is still this chapter 1, that's the old information, but still important, okay? Still important because this is the like a reminder, we just recalling the information because we will definitely ask for the vertical asymptotes. Okay, let's look at this now. That's what I said. We will look at the behavior as x becomes really big in the positive or negative direction, and we will call end behavior. And I would like to take this function. Oh, okay. That means we probably remember the simplest rational function, 1 over x. 0 is not in the domain. We see right away. That means we can investigate 0. This, and we know 1 over 0, infinity, 1 over 0, infinity, 1 over small big, 1 over small big, which in this case, one of them should be positive. In this case, this is positive infinity, this is negative infinity, and we do have a conclusion. X equals to 0 is a vertical asymptote because of that. Okay, but I also want to check how this function behaves at infinity, as x approaches infinity or negative infinity, which we will call limits at infinity. And having a graph, we can see as x is getting bigger and bigger and bigger, the whole fraction, the whole output, it's smaller and smaller, right? Like 1 over x, 1 over 10, 1 over 100, 1 over, I don't know, 10,000, 1 over million. Always when we divide by the huge number, 1 over huge number is a small number. That means this is 0 and this is also 0. This goes through the negative, we can see from the below the x-axis, but it's also approaching 0, that line, which is x-axis. Okay, and the conclusion, actually, okay, I didn't type this. The conclusion is, if the limit at infinity, positive or negative, is a finite number, even 0, like this one, we can say that this number will give me horizontal asymptote. Okay, and we can see we do have horizontal asymptote. Definitely, right? I can even do the dotted line. That's what we do for the asymptotes. Okay? That means always this number, if this is a finite number, for the limit at infinity is giving me the finite number, then this number, this value is a horizontal asymptote. Yeah, that we can see the difference. Now, if we would like to make sure that we understand the concept, this slide is really good. You can pause the video and look at this. Okay, the main concept, it's covered. Let's look at this. And now I will have just the information definition. That means let f to be a function defined on some interval from a to infinity. That we can see that the end of the domain is infinity. Then the limit of the function at infinity is just a finite number L. And this we know that this means that if x is getting really, really big, the whole value is not going to be greater or smaller than L. It's approaching L. And the same on, yeah, this is just what I said. The same you can have on the negative side. If if x approaches negative infinity, the whole value could also approach L. Sufficiently large negative numbers will give me like a limit L. Now, just the definition of the horizontal asymptote, computing a limit at positive infinity and negative infinity, and we may have different values, also please note, okay, because we may actually have the maximum number of horizontal asymptote could be actually 2, because we're computing limit at positive and negative infinity. But if we have finite number, we call this line, this horizontal line, we call a horizontal asymptote. Okay, that means the other way. How can we find the horizontal asymptote? We have to compute a limit at infinity, positive and negative. And let's look at some graphs. Okay, some of them are typical, some of them are a little bit weird. That means let's see. 1, 2, 3, 4, 5, and 6. That means let's look at 2. 2 looks like a typical, you can see function at positive infinity. It's not gonna be, it's approaching the horizontal line L. The values are not gonna be lower than L. L is definitely an asymptote. We can see number 3 is a little bit weird, okay? Because function is it's kind of like a snake getting closer and closer and closer, like oscillating between L. But we will also call that this is an asymptote. That means, please note, we may sometimes have the intersection with an asymptote. The only thing that is important, the curve can't really intersect the asymptote at infinity. I mean, this is really, really special case because we'll be like constantly intersecting, but it will be like getting closer and closer and closer to the line L. Okay, like let's look at maybe this one, okay? Or even the first one, We have the intersection, but that's not really important. At infinity, the blue line will never meet with the pink line. The blue curve never will meet the pink line. That means this is definitely a horizontal asymptote. And this one also, that means don't worry if you have to draw a function, because we will try to draw some functions, and you will see, oh, I have to intersect, that's fine. You can intersect the horizontal asymptote, but not at positive or negative infinity, depends what we calculated. And number 6 is the example with 2 asymptotes. One of them is at negative infinity, we can see 2, and one of them, negative 1, is at positive infinity. That's what we have to respect. Okay. Now let's try to calculate the limits. Before we start, let's look at this property, this theorem, okay? Because this will be a really helpful limit or formula. For a positive number, like r, it's positive, greater than 0. Okay? I wanted to use my own words. Okay, let me just read it. If r is greater than 0, it's a rational number. That means r is the rational number, but greater than 0, positive, such that x to the power of r is defined for all of the x's. Okay? That means we want this to be positive, but x could be any number. That means now what's happened? What we have? We have this type of function, 1 over x to the power of r. 1 over x to the power of r. Okay? R is positive. That's what I wanted to indicate. And now, if x is getting bigger and bigger, and even if I will take to the power of 1, 2, 3, 4, 5, 1/2, 1/3, like any positive number, I will create even bigger, if the number is, of course, greater than 1 r. I will create even bigger denominator. Right? That means 1, theoretically, over infinity, it's always 0. I mean, I can write a really informal fraction. 1 over big, it's small. Please remember this. That means 1 over huge number, it's no, we know the behavior, it's 0. Or the same on this side. On this side, the only thing is x will be negative. That means we will get that 0, but through the negative values. Okay? But it's the same idea. 1 over big numbers, because this will be big negative. Or if r is even, we will still get positive, depends on the function. But 1 over infinity, 1, I can write this way, but it's not really formal. Yeah? I prefer this one because this will tell me a little bit more. 1 over big number is always small. Small is 0, big is infinity. I will remove this one. Okay? That means please remember this, because now we will start calculating more complex limits. And we will definitely use this property. Probably it's not even for you, it's not even the new stuff, it's just a common thing, common arithmetic. Okay, examples. We have a limit as x approaches infinity, 1 over x minus 5. That means, what do you think? What is this limit? Do you think you can tell me, or? Okay, we can try. You can try to, maybe later you can give me a little bit faster answer. Okay, if I will think that x is huge number, subtracting 5 or adding 5 or any other values, they not really, this is not really affecting my infinity. It's still 1 over huge number, 1 over infinity. That means 1 over infinity is 0, right? That's what I would like you to know. And that right away. I will show you a few algebra steps, but don't worry, okay? If you can see this right away, that's fine. Okay? That's what we will do. Looking at this rational function, 1, of course, is 1, nothing to do. But x is the highest, is the leading function. That means we're looking at this, we have to pick up the leading function, which in this case is just x, and I will factor out. That means, can you see what I did? I factor out x. X times 1 is x. X times 5 over x, it's still 5. If I will cancel out. But then what I see this 5 over big number is just 0. This is 1 and 1, and this actually is also 1 over big number. That we can see, excuse me, we can see a little bit like more clear using the previous slide, using the previous theorem. Yes, 1 over infinity. That's what we can see. But don't worry, if you can see this right away, you can give me that answer. Okay, what about this one? Limit as x approaches infinity, 2x minus 1 over 4x squared plus 5. Okay? The same thing. For now, I am not sure. Okay, because we can see if I have, now it's even more complicated because it looks like I have infinity on the top and I have infinity in the denominator. And we still don't know, but if you're gonna take the calculus 2 with me or with any other instructor, this is actually the topic for calculus 2, infinity over infinity. It's huge, yeah, we call indeterminate form, and we can't just cancel out. We can't just say 1 or 0 or infinity. We really have to do things. And we have special tools. But even for this class, if we have this type of infinity, we can do it. That means I will use the same steps that I did for number 1. I will pick the leading function, or maybe just the function without the coefficient, x and x squared. And let's factor out. I did factor out x, and I did factor out x squared in the denominator. X times 2 is giving me back 2x. X times 1 over x is 1. That means that's correct. And the same here. If I distribute, I will have 4x squared plus 5. Okay, but now we can see 1 over x goes to 0. 5 over x squared also goes to 0. Doesn't matter that it's 5. Denominator is showing me a huge number. And then I can simplify this and I will have 1 over x. I can We can see, because this is only 2/4 finite number, not really important when I compare to the infinity. That means x over x squared is 1/x, and 1/x also goes to 0. Okay, number 3. Let's keep moving because I have lots of different types. 5x cubed plus x squared minus x to the power of 4 minus x cubed plus 3. The same thing, we have to focus, I can even circle, just on the leading function. Let's factor out, okay, and let's see what's happened. This goes to 0, this goes to 0, this goes to 0, this goes to 0. Everything goes to 0. 5/1, okay, just the final. And this one, x cubed over x to the power of 4, it is 1/x, and also goes to 0. Okay, oh, a little bit better. That means this is my type 1. And what do you think? What is the main conclusion of this? All of the limits were 0. And can you tell me, with respect to the degree of the polynomials, which degree was higher, in the numerator or denominator? In the denominator. Thank you, Adam. Thank you, Joey. Yes. That means you can see, if we will set up a battle between the degree of the polynomials from the top and the bottom, which means numerator and denominator, and if the denominator is winning, always limit will be 0. Okay? If degree is less in the numerator, then the limit, this type of limit, of course, at infinity or negative infinity, it's always 0. Please remember, that means if you will remember this, you do have the proof, the arithmetic proof, the algebra proof, but you may all remember this and you will be more efficient. Okay, and then I have exam type question. Can you tell me this limit? Three x to the power of 5 over x to the power of 7. Because we just learned the rest of the terms, if I will follow these steps, they are not important because they will become 0. Limits at infinity of the rational function telling me that I have to focus on the leading function, leading terms on the top and on the bottom. That means what is this limit? Oh, nobody wants to type the easy answer. 0, thank you. The limit is 0. Great. Let's keep moving. Number 5. Wow, what about this one? Limit at infinity, 3x plus 5 over x minus 4. Okay, do you think what's the answer? We can try, okay, if we're not sure, because again, I will solve 3 problems and hopefully you will give me the conclusion and then you will know the answer right away of types like that. This one, fortunately or unfortunately, the degree is actually the same. But let's see what's happened when I factor out, because I can do the same step. I'm factoring out this leading function. I have 3 left and 1, and the other parts, of course, are 0. This goes to 0, and this goes to 0. And what's happened, I can use different color, I can cancel out because they are the same function, exactly the same degree. And what's left? Can you tell me the answer of this limit? This is just simply 1, 1. This goes to 0. And what's left? 3 over 1, which is 3. That means, okay, I don't want to make the conclusion, but 3 over 1, it's simply a ratio of the leading coefficient. Okay, what about this one? Do you think you can give me the answer? It's, oh, we have to be careful, Adam. Almost correct. What is the leading coefficient on the top? I'm happy with that. 5, yes, negative. I'm happy with 5, but we have to, yeah, oh, I just want to circle. Yeah. But we can see, first of all, it's important. Let me circle the function. X squared and x squared, that's my leading functions. Let's factor out. this goes to 0, this goes to 0, and x squared will be cancelled out. No problem. And negative 3 over 5 stays, and that's the answer. Right? That we can see how fast we can do. Again, remember, limits at infinity, the leading terms are the most important, because algebraically we proved the rest of them become 0 eventually. Okay, and what about this one? Limit as x goes to negative infinity, it's still fine. Can you tell me the answer? No? I know that you can tell me. Thank you very much. We're just looking at the leading functions, they are the same. That means I did my math, but we can see 0, 0, 0, 0. This is just cancel out, and 4 over 7 stays. Okay. One more comment. If this is the finite number, I can say that line is a horizontal asymptote. Yeah, just in case. That line, horizontal line, this value, it's a horizontal asymptote. Because we're focusing on computing, but still the concept is important. This line is a horizontal asymptote. Okay, and now this is the statement. If degree of the polynomial in the numerator and denominator is the same, then the limit is just a ratio, my extra, of leading coefficients. Okay? Okay, now are you ready for your exam type question? Who can give me the answer of this one? Have to be careful. Limit as x goes to infinity, 4x to the power of 4 plus 5, x squared minus 2 times 4x squared minus 1. Okay, I can give you a few seconds. Or, you know the limit. No, come on, you have to tell me. Limit, it's 1. Thank you, Chris. Thank you, Adam. Yes, the limit is 1. Because what we have? We do have 4x to the power of 4, and I can maybe write this way. The rest of them we're not looking, because we know what's going on. And if I distribute everything, the highest power will be, oh, no. What I did, okay, I was just trying, okay, it's too low. If I multiply these two, 4x squared times x squared is 4x to the power of 4. And the rest of them will be with the lower power. And it's the same function, 4 over 4, the ratio of the leading coefficients, it's of course 1. Okay, that means please be really, really careful. Right? Okay, let's keep moving. Now, it's still the same type, but I kind of changed the functions a little bit. That's what I'm doing. I'm trying to make the ratio not necessarily of two polynomials. One of them will be like a root function. That's what do you think? What's the degree of the function from the numerator? Can you tell me the degree of the function from the numerator? It's just 1. Thank you. Now, if I have to say the degree of the function from the denominator, what will be the degree? What is the degree of this function? Yeah, do you think you can? We can see it's the 9x squared, however, is the square root of this. That's what I'm doing. I'm still trying to do my math, okay? But you will probably be a little bit more efficient after this. That means I factor out x, that's what we know how to do, and I factor out x squared, but everything is under the square root, okay? And now, oh, too fast, square root of x squared, if x is positive infinity, it's just x. That means this quantity is just x. And now, x and x, I can cancel out. That's the same thing. And of course, this goes to 0, this goes to 0, 1 over square root of 9. I actually wanted to write this, which is 1 over 3. That's we can see, even looking at this, we can say right away, is the square root of 9 and square root of x squared, which will give me x, if x is positive. Right? That means this is degree 1 and this is degree 1. 1 over 3. Okay, what about this one? Can you tell me this limit? Now we know what to do. We're not changing anything, but what you will change here? I can write down x is positive. That means I have 8x and something. And this, what is square root of 4? 2, and then square root of x squared. And the rest of them I don't, I'm just looking at my leading functions. And that means I have 2x over 8x. Okay, the same, it's simply 1/4. Thank you. The only thing that we have to be extremely careful, because what we dealing with the square roots, we're doing something like that, right? Square root of x squared, we're simplifying and it's saying x. And this is perfectly fine if and only if x is positive or equals to 0. Right? Because if that x is negative, we could have a negative number, like let's say this. Okay? Negative 5 squared, I can have it. I will not copy, that's not the right answer. Right? That means if this x is positive, no problem. I can simplify like that. I don't even have to square that 5 and then they take the square root. We know that this cancel out, it's just 5. But if we have negative, I can copy the same number, but I have to put extra negative. Because we know that it's gonna be 5 also. That means copy the same number, x, and put extra negative. If x is negative. Okay? That means now let's see. Actually, I can show you this before we solve it. That's actually the same thing. And please remember, because the answers, that the question on the test will be just the difference, positive or negative, but it's really a concept. That we can simply simplify this way if x is positive, but if x is negative, which means in our case, x goes to negative infinity, this one is positive. Okay? Then we have to be careful, and we always have to say this, we can simplify, but we have to put extra negative. Because having extra negative, I have positive number. And now we can see the same function, but at negative infinity. That we will follow the same thing, limit, square root of 4, I can write actually, and we will have this. And then minus, or also minus, that's fine. And I have limit as x goes to negative infinity, I have 8x, and square root of x squared is just negative x, which it is positive, yeah, because this is negative, with this negative is still positive. That means the answer is negative 1/4. Right? Please always note the negative infinity. Okay. Let's keep moving. Oh, I have 17, I mean from 12 to 17, 6 problems. Do you think you can give me the answer? Let's work it out the degree. This is, because all of them are limits at infinity, positive or negative, that's when we have to be careful, okay? And then we have to figure out the degree. That means this is degree 1, 8x to the power of 1. What about this one? How can you simplify this? Because we're only looking at the leading terms. 5th root of, oh yeah, I think that's the Chris, right? I think that's the correct answer, 1/4. Oh, hang on, that was the answer. Am I crazy? that's the answer from the previous, right? Because my chat box moved and I thought that you typed again. No, okay, let's see. Let's actually see. Okay, we do have the fifth root, right? That's mean, what is the fifth root of 32? Do you know that number? Oh, you don't know? It's 2. I will not ask you weird questions. 2 times 2 times 2 times 2 times 2, 5 times will be 32. And now I have fifth root of x to the power of 5. Of course, is x. 2 over 8, it's 1/4. Okay? Now I am asking this question as an additional one, because this one is at negative infinity. Right? That's what and it's the same function. And what do you think? Are we gonna have negative 1/4 or it will stay positive 1/4? No? Yeah, that's of course, it's a tricky question, because we have to notice that now we have an odd root. If we have the odd root, we're not changing anything, because we can accept negative numbers under the odd root. Okay? That means we will have the same way and the answer will be still 1/4. Okay? Please remember, odd root is not affected by negative numbers. It's still negative. Or how you can also check. Let's look at this. You will also like this. This is also a good tool. X is negative infinity, right? That means x goes to negative infinity. If I think about the big negative numbers in the denominator, that means, what do you think? What sign I will have? 8 times big negative numbers plus 105. Am I gonna get positive number or negative number? Oh, you can type. Oh, 8 times huge negative numbers plus 105. Now, you must know, this is negative number, right? 8 times negative, but it's huge, plus 105. Okay, that means this will give me negative number, okay? And if I will take negative number to the power of 5 and the fifth root, I will also have negative number. That means negative number over negative number, I have to get positive answer, right? I have to. Or we can even look at this, the first one. That's also another way to check if my sign is correct. Positive. That means this is positive and this is positive. Positive over positive is also positive. No problem. Okay. Now let's look at this one. X to the power of 6 and cube root of this will give me just x squared. Cube root of 8 is 2. Okay. Limit at positive infinity, I have no problem. The answer is 1/2. Okay. Now limit at negative infinity and I have even root. That means I can copy. Okay. I can copy denominator 2x, but I have to simplify this. Square root of 16 is 4, and square root of x squared will give me negative x. Okay, we remember this will give me negative x because x is negative. If x is negative, negative and negative, it's still positive. Okay, that means please note this. And the final answer is -2, if I simplify. Okay, another even root and another negative infinity. But let's see. Square root of 9, it's 3, because we're only looking at this. And square root of x to the power of 6, x cubed. Limit as x goes to negative infinity. And square root of x to the power of 6, I can divide 6 by 2. I will have x squared. But since it's negative, I will keep negative x, because we remember we have to have the positive. Dividing by 2 will give me 3. Am I right? I did put 2. 6 divided by 2 is 3. Okay, And then I do have negative 3 x cubed over x cubed, just negative 3. Of course, still indicating negative infinity. Okay, that's we can see. Now, let's look at this one. Still negative infinity. And let's see. 8x squared, and we don't care for the rest of them. And now, square root of 16 is 4. Square root of x to the power of 4. And let's see what's happened. Okay, 8x, 4. Square root of x to the power of 4, 4 I can divide by 2, I will have x squared. But since it's negative infinity, I have to have this negative. But can you see what's happened? We do have extra squared, positive, like even exponent. That means this is fine. I mean, at the final step, it's giving me negative squared is positive. That means actually, oh, that's squared. The same degree, 4 over 8 half. All right, that means this will be really important page, what I would like to indicate. Even if it is negative infinity, it's still positive answer. And this one is still positive because the negative was squared. We did have extra like power, 2 powers because it's squared. Or again, if please remember, okay, I will repeat the same what I said in the first line. Looking at the final answers, positive, positive, negative, negative, and so on. You can always do the final check of the final sign. That means you can follow the definition, of course, but always check the sign. Looking at question 16, we can see limit as x goes to negative infinity. If I put negative infinity to the power of 4, huge number negative to the power of even exponent will give me positive, or the square root. X squared in the denominator, I will be squaring negative numbers, always positive. Positive over positive, function behaves at negative infinity as a positive number. We know the coefficient, we know the value 1/2, but you will never make mistake if you will test this way. Or we can even look at this one. I can maybe skip this. If we will simplify, I will have square root of 4 is 2, and x to the power of 6 divided by 2 is x cubed. Okay, and then it's 4x cubed. That means I definitely have the same degree. 2 over 4, it's actually half. Right? 2 over 4 is half. But now, can you tell me if this is positive or negative answer? It will be positive or negative. Do you think you can tell me? Maybe the session is too late. Maybe the morning session are better. Okay, we can do the same thing. We have x to the power, it's negative, right? Because it's at negative infinity, x cubed will give me negative number, x to the power of 6 will give me positive. The final answer must be negative. That means if we can figure out the coefficient, the ratio, we can work it out on the sign this way, yeah? Instead of like using the definition. Okay, important slide. You can pause the video, take a paper, take a pencil, and try to solve it again. Okay. Let's see this. Okay, I do have 3 limits like that. How functions sine of x, that means this one are totally different. Yes, we went through all of these rational functions and we should be okay. Now let's look at different things. Sine of x, that means how functions sine of x behaves at infinity. What do you think? Do we have a limit, this limit exists or not? You can type the answer and I will draw the sine. And the sine curve behaves like that. Pi, 2 pi, 3 pi, 0, pi over 2, 3 pi over 2, 5 pi over 2, maximum value 1, minimum value -1, and so on, of course. Okay? As we can see, it's like 1 and then -1, 1 and -1. That means I can write something like that. It's like oscillating, +1, -1, positive, -1. That means I can simply say that this limit doesn't exist as a one finite number. Simply is undefined. Please remember that. Okay, 19, sine. Since sine is continuous function, I can focus first of all on the inside limit, right? I can apply to the inner function, and 1 over x, 1 over big number is small, sine at 0 is 0. That means this one is simple, okay? And this one we will skip because it's Math 141. Okay, if you're gonna take the math, I will explain. We can probably do it, but it was in your textbook. I mean, it was in chapter 3. Yeah, I don't know. I mean, I do know the way, but we will not ask because that's typical limit for Math 141. Typical function. Okay, but remember this one, because sometimes we don't know what to do, right? The limit doesn't exist. And then we have another types that if we computing a limit at infinity, positive or negative of the function, we actually getting the infinite limit. Yeah, that means no bounds. One of the nice example is x cubed. Function x cubed looks like that. And we can see limit of x cubed at positive infinity. It's simply positive infinity. I will cube the huge number. I will have another huge number. And if I will cube negative infinity, I will have negative infinity. That means when we getting like the infinite limits at infinity, this means no horizontal asymptotes, because that's another thing. All of the limits that we compute and we got a finite number, all of these finite numbers are the horizontal asymptotes, not case like that. Okay, and then I have I have x cubed. We know that this is positive infinity, this is negative infinity. I'm just looking because the same, this one, I took from you, it's more Math 141, okay? Even this one, because what we have, okay, maybe 23 we can do it. Why I'm saying Math 141? Because it's the next level. If we will take this infinity and we will think what we will have infinity squared, this infinity, and then minus infinity. That means you remember I did write before like infinity over infinity, and I said it's indeterminate form. In mathematics, we do have 7 indeterminate forms, and this is one of them, and actually infinity minus infinity is another one. Okay, that means we have to remember infinity minus infinity could be 0, I don't know, could be the finite number, like let's say L, could be infinity or could be negative infinity. That means at the moment it's like indeterminate. We really have to do something to prove what it is, right? Let's say C like constant. We may have even the finite number. That means this one is too complicated, but this one possibly we can figure out the way that we just did. I will factor out x squared and I will have 1 minus x over x squared. And I know that x over x squared will go to 0, and I will only end up with x squared, which is infinity, times 1. Now I don't really have infinity minus infinity. That means since this is huge number, the final answer is infinity. But don't worry, it was in your textbook, because all of the problems came from the section 3.4. I would say this is also, it's a little bit easier, but it's also Math 141. Because you will see, I will teach you some really nice, fantastic tools to deal with this. Okay? But yeah, we still know that we can factor out the leading function. Okay? Okay, but that's just the examples of limit infinite limit at infinity. Okay, let's see what else I have. Oh, that's another like infinite limits at infinity, but the rational functions. That means now we can see we have rational functions, all of them at positive, negative, infinity. We will focus on that. And let's look at the first one. 2x cubed plus x plus 1, x squared minus 10. That means I'm still interested at the leading. Yeah. And it's at infinity. That means having 2x cubed, and maybe I can write this way, and the rest of the stuff, if I will factor out, and x squared, and the rest of the stuff. We know that they will go to 0. You can see I can cancel out everything, not everything, x squared and x cubed will give me just x, and I will just get 2x, right? Because we can see right away, focusing on the leading function, 2x cubed over x squared will give me 2x. X is positive infinity, answer is positive infinity. Okay? Now, can you tell me this limit? This limit is at negative infinity, and what do you think? Limit as x goes to negative infinity, if I cancel out 4x squared over x, I will have 4x. That means what is this answer? Oh, x is negative infinity. Big number, negative times 4 is negative infinity. Okay? Nobody wants to try? It's a good moment to even make mistakes. Later will be too late. Okay, now limit at infinity, and then that's my leading function, and this is my leading function. Okay, who can tell me this one? Limit at infinity, and I have negative x squared over 20x, because we know the rest of them will go to infinity, to 0, the rest of the terms. Limit at infinity. I can cancel out 1x. That means, what is this answer? We still have x, infinity, but we have negative. Negative and negative infinity instead of x will give me positive infinity. Dividing by 20 is not sufficient. I mean, it's not really, doesn't affect the answer. That we can see if we have, again, the battle between the degrees of the denominator and numerator, and if the top of the function is winning, numerator, always infinity. But remember about the arithmetic, negative, negative, positive, and so on. Oh? You can pause the video if you like a little bit slower. Okay, now let's see what I have. Okay, that means that's everything for my limits, but I do have 1 or 2 questions, and we will be done. Yeah, sketch the graph of the following function by finding its intercepts and its limits at infinity. That's me. What do you think? What is the limit as x goes to positive infinity of the function y? Let me just say this, I don't want to cancel out. I think first of all, we can see nothing to, it's just multiplication of the numbers, right? That means we definitely have no horizontal asymptote because I'm not gonna get a finite number. If x is huge number, huge number, huge number, huge number. Huge number minus 2 to the power of 4 is the huge number. Huge number plus 1 cube, it's huge number. Huge number minus 1 is a huge number. Huge number times another huge number, it's huge number. That means at positive infinity, this function goes up, right? Now, how this function behaves at negative infinity, my function y. Now let's see, I do have even exponent. That means whatever I will substitute, I will always have positive, huge number positive. Now I do have cube. That means this will give me negative huge number. I can write positive huge number. Okay, and this is also to the power of odd number 1, huge number minus 1, negative huge number minus 1 is negative number. That means negative times positive, it's negative huge number. Okay, that's we can see how we can really get, it's nice function, it's just a polynomial. It's really high degree, but we can figure out these values. And shall we try to draw it? Okay, who can tell me x-intercepts? You have to tell me. What are the x-intercepts? Looking at this, at this formula, what value of x will give me 0? Negative 1, positive 1, and 2, really good. 2, negative 1, and 1. I will go by order. It's really good, Adam, thank you. That we do have negative 1. Negative 1 came actually from here. We do have 1, and we have 2. Really good, because these numbers will give me 0. Okay, who can tell me the y-intercept? That's the x-intercepts, and that's the y-intercept. Computing y-intercept, probably is a huge number, but or maybe not really. X is 0. That means this is 0, this is 0, and this is 0. What we have? We do have negative 2 to the power of 4. We have 1 cube, which of course is, and we have negative 1. Oh, who can help me with the arithmetic? Negative 2 to the power of 4 is 16, positive 16. Negative 1 will give me negative. Okay, that means somewhere here, negative 16. Okay, and let's see. We know what we know. X-intercept means that we intersecting, the graph will intersect x-axis. Let's look at this one, x minus 1. X minus 1 is the easiest one. 1 came from this one because we have no power, nothing. That means we simply have to intersect. I still don't know if this will be like that or maybe like that. Okay, I don't know if it's from above to below or below to above. But this is simply intersection. Now, at negative 1, we will also intersect, but since this is cube, function will become like more flatter. As if this power, if this exponent is bigger, function becomes like more flat at this point. Okay? And now, if we have even bigger exponent, but that's will be more, even more flat. But what is important, this is an even number, even exponent. Okay? If it's even, at this point, we never intersect. We just touching a function. I mean, touching the x-axis, maybe above, maybe below. Okay, that we know what to do at each single x-intercept. Look at the infinities. At infinity, function is infinity. That means function will go up. And at negative infinity, function will go, oh, actually, is this negative infinity? This should be positive infinity. You're not correcting me, because we do have this will give me positive infinity, this is negative infinity, and this is negative infinity. Negative times negative is positive. Yes, you should. Yeah, you should tell me if I sometimes it's I'm sitting probably too close to my laptop. Yeah, and this is positive infinity. That means when function is if x approaches negative infinity, function will go up. Okay, that means let's start drawing. What's happened? At negative 1, it's flat. That means I will intersect, but I will make flat. And then my y-intercept. This one was just fine. Oh no, something is... Am I crazy? Because I have to okay, I'm not intersecting at 2. This is correct. I thought that I will be intersecting and I will be not on the top. But as I said, we have to be a little bit, because it's to the power of 4, flat. Okay, and this is positive infinity and this is positive infinity. Okay, That means based on the limits and some values, we have the graph. And I think I have the graph for you. Okay, and then I do have one thing. Just I have two functions. Okay, find all vertical and horizontal asymptotes of the following function, and I will give you this one: x squared minus 9, x plus 2, and x minus 3. Okay, that means vertical asymptotes, the potential vertical asymptotes, are the numbers that are not in the domain of the function. Right? Because we can see -2 is not in the domain and 3 is not in the domain. But we have to be careful, we can't list them right away. Okay, vertical asymptotes, but potential, we still don't know. What we have to do, we have to try to compute a limit. Okay, limit at, let's say -2 of this function. I can factor out, okay, because it's an important question, because you will right away put -2 and 3. Maybe, but I don't know, I have to check this. X minus 3, x plus 3, x plus 2, x minus 3. Okay, first of all, I see that I can cancel out this, and then limit at -2, I will substitute -2. -2 plus 3, it's just +1. -2 plus 2 is 0. That means 1 over 0, 1 over like small number will give me big number, give me infinity. Of course, I have to make sure if this is -2 from the right-hand side, this will be like -1.9 plus 2 will give me positive. That means it's enough, because it's enough to prove that one limit is infinity. That means this is definitely a vertical asymptote at -2. Okay? But computing a limit at +3, let's see if we get infinity. I can actually get the simplest form. You can see I am just taking x plus 3, x plus 2, 3 plus 3, 6, 3 plus 2, 5. Are we getting infinity? I can write like that. This is different than infinity. That's what we have. We have removable discontinuity. This is not a vertical asymptote. That means please always remember, right? You have to compute the limits, or again, algebraically, if you can cancel out completely a function. Can you see? I did get rid of that 0. Of course, function is still undefined at 3, but I cancel out my fraction at the moment. And only x plus 2, which -2 is the 0, only this stays. That means only this will be a vertical asymptote. Okay? Do not pick the answer with the other one. Okay, and now who can tell me horizontal, and we done. I will finish the session. But you have to, everybody has to type horizontal asymptote for me. Horizontal. Horizontal asymptote. Y equals to what? Okay, we do have the first answer, 1. Everybody can confirm that. That's the function. 1, 0, or maybe none. Look at the function. Okay, hopefully after that 1 hour, we know. We can see what we have. We do have 1x squared. In order to find the horizontal asymptote, we have to compute a limit at infinity. Okay? And I see x squared, not important. When I multiply, when I distribute everything from the denominator, I will have x squared and the rest of them. X squared and x squared, the same function, leading coefficients 1 over 1. 1. Thank you, Adam. That was the correct answer. That means make sure that you know the vertical asymptotes and the horizontal asymptotes. Okay, thank you very much. I did put extra practice for the vertical and horizontal asymptotes, like, you know, in the last module, practice with Kasia. You can double check. And of course, make sure that you know every single limit at infinity from this session. Thank you.